Hey everyone, welcome to exercise 9.3. Today we're going to be taking a look at sketching parabolas. Now, parabolas have some key features, and the first one we're going to take a look at is, what are they, and also what does dilation mean? So if we were to sketch a parabola, it doesn't necessarily show the plotted points, okay? Just like when we're sketching a linear line, we just need 2 points to sketch a linear line. Now with a parabola, all we need to identify are the key features such as the X and Y intercepts and the turning point. Now, sometimes you might not have X and Y intercepts, okay? It might just be floating in one of the quadrants, but it'll always have a turning point. Otherwise, it won't be a parabola, okay? It'll just be a linear line. The basic quadratic graph has the equation y equals x squared, and that's basically the equivalent to the linear line y equals x, where you just have a straight line crossing the origin. Y equals x squared, as you can see down here in the blue, that's just the generic example that we do for a parabola as an introduction. There's some things we can observe about these sort of parabolas or quadratic lines, and the three are dilation, translation, and reflection. Dilation is the one that we're going to take a look at first. So if we take a look at the graph to our right, we've got y equals x squared, which is pretty generic. And if we add a coefficient of 2 in front of the x squared, what you'll notice is you'll get a narrower parabola. What happens though is if we have a fractional coefficient, whether it's positive or negative, it's going to be a wider dilation, okay? So if it's any whole number that's greater than 1 or less than -1, okay, we're going to have a narrower dilation. If we have any fraction that's in the positives or negatives, we're going to get a wider dilation. So example 1, identify which equation is narrower or wider. So here in A, we've got y equals 1 on 5 x squared. So compared to y equals x squared, this one here is going to be wider. Let me just pause this so I can show you. Right, so what you can see here is I've put the graph into Desmos for us to all see. Now, if we zoom in on this graph, key note here is in red, we've got y equals x squared, okay, the generic quadratic example. And then if we have y equals 1/5 x squared, then it becomes wider, which is the blue line, okay, which is our equation here. Let's take a look at the next one. Y equals 4x squared. This one here is going to be narrower because it's a whole number that's greater than 1. And it doesn't have to be a whole number. It can just be any number that's greater than 1 or less than -1, and it'll be narrower. All right. So just to show you on the graph, let me just pause this again. Right, and I've sketched the two comparisons on Desmos once again. Again, we're just identifying whether or not the y equals 4x squared is narrower or wider. And as you can see here in blue, we've got y equals 4x squared. That's within the y equals x squared line, so it is therefore narrower. Right, so the next one we take a look at is vertical translation, and this is where we have a constant in our equation, okay? A constant is just a number by itself without any pronumerals attached. Here we see x squared plus 2, y equals x squared plus 2 compared with y equals x squared, and it simply just shifts up the y-axis where the turning point is at 0, 2. So 2 places above the origin of the original y equals x squared turning point. So here what we can do is state the vertical translation of the coordinates of the turning point for the graphs of the following equations when compared to the graph of y equals x squared. So once again, we're comparing it to y equals x squared, and we need to state the vertical translation and the coordinates of the turning point. Okay, so the turning point is simply just when the graph or the parabola turns from a negative gradient into a positive gradient. So here we have y equals x squared plus 5. The plus 5 is our constant, which indicates that there's going to be a vertical translation where we move up 5 from the origin. Up 5 units. Okay, and our turning point TP is going to be at 0, 5 because our y coordinate value will now be 5. Okay, just like where we had y equals x squared plus 2, the 0, 2, this 2 came from this constant of 2. Here we've got a constant of 5, so it'll be 3 units higher than this 0, 2, or 5 higher from the origin. I'll crop a Desmos graph afterwards, so you can see just exactly where it is. The next one here, y equals x squared take away 4, so our vertical translation. This is going to go down because it's negative. So previously it was a plus 5. Now we've got a negative 4 constant. So down 4 units. Okay, and our turning point will be 0, negative 4. All right, let's put this on the graph and we'll see what it looks like. Alrighty, now that we've got our graph in blue, so our y equals x squared plus 5, we can see the blue parabola is 5 units up from the origin, okay, where the turning point's at 0, 5. Over here, we've got y equals x squared take away 4 in blue, and we can see it's below the origin 4 units, okay, and yeah, that's the visualization of what we just covered. Horizontal translation. Now, this is where we have it in the turning point form. So remember back in chapter 7, where we were learning about completing the square and getting it into the turning point form, or even in chapter 8, I think there was some turning point form equations, and also some sketching later on that we're going to see in chapter 9. So horizontal translation. If we take a look at the two examples, y equals brackets x take away 2 squared, compared to y equals x squared, this is going to shift the turning point or the parabola 2 units to the right, okay? Vice versa, when we translate y equals x plus 1, because it's a plus, we move it to the left. So negatives, we move to the right. Positives, we move to the left. Okay, and that's going to shift the turning point off the origin. Okay, so I'll show you the proof in class, but just for simplicity's sake, okay, negatives to the right, okay, positive to the left when we're in this, I guess, squared bracket situation. So here what we have is another comparison to y equals x squared, and we got to state the horizontal translation and the coordinate of the turning point. Let me just double check if I did that for the top one. Oh no, top one didn't ask. Oh no, and state the turning point of each one. Yeah, so the first one, when we were doing narrow or wider, the turning point didn't change. Okay, so TP 0, 0. Right, let's get back to where we were. So down here, horizontal translation. For A, Because it's a -3, TP moves 3 units to the right of the origin. Again, you didn't have to write all this, but I'm just going to write down what I'm vocalizing. So the turning point here would now be 3 and 0 because we've moved 3 units to the right on the x-axis, and our x value now becomes 3 instead of 0. In B, we've got a +2, so our horizontal translation. This will mean the turning point moves 2 units to the left of the origin. So to the left means we're in the negatives on the x side of the values, and that's why we get a turning point of -2 and 0. Let me just put this up on Desmos so you guys can see it visually. And we're back with the graphs. So here you can see y equals brackets x take away 3 squared. It's shifted the turning point 3 units to the right of the origin. Here in example B, we've got y equals brackets x plus 2 squared. So now we've got a -2 in the x value of the turning point, and the y value stays 0. Okay. Reflection. So sometimes you might get a negative x squared coefficient. So for example, 1 equals -1x squared compared with 1 equals 1x squared. You just get a nice little upside down parabola in the negatives compared to the positives where it's a smiley face. Okay, often teachers call the negatives the unhappy face. Okay, so smiley face for positives, negatives on the x squared coefficient is going to turn it into an unhappy face. So example 4, for each of the graphs, give the coordinates of the turning point. Okay, state whether it is a maximum or a minimum. So we know from the previous exercise, if it's in a brackets, x take away a constant, shut the brackets, in a squared situation, we're in our turning point form. So our turning point here is going to be negatives will shift us to the right. So we're going to have 7, 0 because x will shift into the positive 7 places. But because we have a negative on the outside of the brackets, this is going to be, so actually I forgot to mention maximum and minimum. So down here, as you read, the graph of y equals x squared has a maximum turning point. So maximum, the graph of y equals x squared has a minimum turning point. Okay, this just means it's a smiley face, and the graph of y equals -x squared has a maximum turning point. In other words, this is our unhappy face. But if you think about it, when we have a maximum turning point, the peak of the parabola is a turning point. When we have a minimum turning point, the lowest point, okay, is the turning point. All right, so here, because we have a negative, this means it's been reflected into an unhappy face. And so we are going to have a maximum. So this negative causes us to have a maximum turning point. Right, so give me a moment just to sketch this out. Let me just pause the record. Actually, let's keep going. No, let me just pause. I'll pause it. All right, so we've got the graph of y equals negative x take away 7 in brackets squared. And as you can see here, if we zoom in on it, our turning point is at 7, 0. Okay, so that's 10, 20, 30, 40, 50. That's at 7, 0. And it's a maximum turning point where this point is the highest point in the parabola. And the reason being is we've got a negative on the outside of the brackets, which implies we've got a negative x squared coefficient. The next one here, y equals 5 take away x squared. So what you notice is this 5 here will shift the graph up 5. So shifts the line, the parabola, the turning point, okay, shifts TP up 5 units. All right, the negative here will imply we've got an inverted or a maximum turning point. And so let's write unhappy face. Right, so this means our turning point. Our turning point is going to be at 0, 5. Okay, because that's our constant. The constant always tells us, I guess, in the generic ax squared plus bx plus c form, where we are on the y-intercept. Okay, it's going to change a little bit later on when we get more complicated equations. And then the negative out in front of the x squared coefficient is going to tell us if it's a maximum or a minimum turning point. So whether it's an unhappy face or a happy face. Okay, so here we've established, therefore, a maximum TP, where the turning point here at 0, 5 is the highest point in the parabola. Alrighty. So, putting it all together, for each of the following quadratic equations, state the appropriate dilation, reflection, and translation of the graph of y equals x squared needed to obtain the graphs. Number 2, state the coordinates of the turning point. And then 3, sketch the graph. So, all right, let's go through one by one. Dilation. Reflection. Translation. Okay. Let's do that for this one as well. Right. So the first one we take a look at is y equals brackets x plus 3 squared. Now the dilation is going to be the same as y equals x squared, because if we expanded this out, the first one is, so remember there's 2x plus 3 brackets. So the first expansion phase is x times x, which gets us the x squared. So notice how the coefficient of both this equation and the equation y equals x squared will have a coefficient of 1. So that's why the dilation won't change. The reflection is, well, it's not going to reflect at all. It's just a minimum. So we're going to have a happy face. And then the translation, it's going to shift left 3 units. Okay. State the coordinates of the turning point. So because of all these information that we've collected, all it's doing is it's just shifted left 3 units. So our turning point will be, should be 3, 0, not what I was about to write. 3, 0, and then hence sketch the graph. To save us some time, I've put it together in Desmos. Okay, so just give me a second. All right, and so we've got our graph here where we compare it to, in green, y equals x squared, and then we can see y equals x plus 3 squared. We still have this minimum, okay, reflection. The dilation are still the same, and then we've got a translation of the turning point 3 units to the left because we have the equation in turning point form. If we had a constant outside the brackets, that would shift it up and down. Okay, so maybe you get some of those questions. Alrighty, in B, what we have is a dilation that's going to be narrower. All right, so if you go back to the very top, what we learned was fractional coefficients on the x squared makes them fatter or wider. The dilation on a coefficient larger than 1 or smaller than -1 will make it narrower. Okay, so here we've got a dilation that's narrower. The reflection is now a maximum, so an unhappy face because of the negative. And then the translation, well, none. Okay, doesn't go up or down. So our turning point, okay, our turning point is still the origin. All right, the graph's width just changed. Okay, so it's gotten narrower, and then it's also an unhappy face. So it's been flipped, but it hasn't actually moved. All right, what does that mean? Let's put it into Desmos and we'll sketch it out. Comparison. Just give me a moment. All righty, and as you can see in blue, we've got our little upside down unhappy graph of y equals -2x squared. Okay, and it hasn't shifted off the origin. The turning point is still there. In green, we've got the y equals x squared parabola. And you can see it's narrower, the blue equation that we're dealing with, y equals -2x squared. All right, and that's all for exercise 9.3. Let me know if you have any questions.